Hey guys, Professor Brown here, and this presentation will be for chapter 4.5, which covers formal charges and resonance. Formal charges are a way of assigning a hypothetical charge to an atom in a covalently bonded molecule. They are calculated by using the formula you see here on this slide, where the formal charge on an atom is equal to the number of valence electrons a neutral atom of that element has, minus the number of lone pair electrons a bonded atom has, minus half of the number of bonding electrons that bonded atom has. And so what that means is formal charges really aren't good for anything until the atom is found in a structure. You can't calculate the formal charge on an atom until it's involved in some bonding. So you can't do formal charges until you have a Lewis structure drawn for your atom. On this slide, we have a few examples, and we are going to calculate the formal charge on each of the atoms in the two following compounds. The first compound we see there is nitrate with the NO3 negative formula. And we already have the structure laid out for everything, so we can just start with counting the formal charges from here. To calculate the formal charge with the nitrogen, we're going to follow our formula that says that formal charge, turn my pen on here. Formal charge is equal to the number of valence electrons a neutral atom normally has, minus the number of non-bonding electrons an atom has, minus the half of the number of bonding electrons an atom has. So for nitrogen, a neutral atom of nitrogen normally has 5 valence electrons. In this case, all of the electrons around our nitrogen are bonding electrons. So we're not going to subtract any of the non-bonding. There are no non-bonding electrons to subtract. Then we subtract 1/2 of the number of bonding electrons on that nitrogen. We can see that nitrogen has 4 bonds, so that's 8 total electrons. And of course, once we multiply 1/2 by 8, we will get 4. So the formal charge on nitrogen is equal to 5 minus 0 minus 4. The formal charge on that nitrogen in the nitrate structure is positive 1. Now let's see if we can calculate the formal charges for each of the oxygen. For the first one here, I'm going to do the oxygen with the double bonds here on the top. Oxygen normally has 6 valence electrons. This oxygen in particular has 4 non-bonding electrons. And this oxygen also has 4 bonding electrons. Once we go ahead and do the 1/2 times 4 to get 2, this oxygen's formal charge becomes 6 minus 4 minus 2, or a formal charge of 0. Now we will do this oxygen here. Oxygen normally has 6 valence electrons. This oxygen has 6 non-bonding electrons, and this oxygen has 2 bonding electrons. Once we reduce the 1/2 times 2, the formal charge on this oxygen becomes 6 minus 1. This gives a -1 for the formal charge on that oxygen. We can probably see that the other oxygen here will closely match that of the oxygen here, and we can pretty much say that they have the same pattern, so they would look exactly the same. So if we wanted to note the formal charges on each of these atoms in our structure, we can erase everything. And we have shown here that our nitrogen has a +1 formal charge. This oxygen has a 0 formal charge, and each of these have -1 formal charge. Now it's important to stop and say that these are not actual charges on these atoms. It's just a way of keeping track of some of the bonding. For our second molecule down here, this is a molecule of methanol, and we will calculate the formal charge on each of the atoms that we see here. We actually need a new space for our H's here because we have two different kinds of H's in this molecule. We have one bonded to an oxygen and 3 others bonded to carbon. Let's do the hydrogen bonded to the oxygen first. Hydrogen normally has 1 valence electron. This hydrogen has 0 non-bonding electrons, and it has 2 bonding electrons. So the formal charge on that hydrogen is 0. For the other hydrogens, they also have 1 valence electron. They also have 0 non-bonding electrons, and they also have 2 bonding electrons. So the formal charges on all of our hydrogens are 0. For carbon, carbon normally has 4 valence electrons. This carbon in particular has 0 non-bonding electrons, and this carbon has 8 bonding electrons from the 4 bonds it shares to the H's and the O. Once you calculate that out, the carbon has a formal charge of 0. In this particular molecule, our oxygen, which normally has 6 valence electrons, has 4 non-bonding electrons and also has 4 bonding electrons. Once the arithmetic is finished there, we can see that the formal charge on that oxygen is 0. In these examples, we have shown how to calculate formal charges for atoms found in a molecule. Again, I want to stress these are not actual charges that exist on these molecules. They are rather what we call a formal charge, which is a way of keeping track of electrons in a molecule. So if formal charges are not telling us something physical or actual about the atom, what are they good for and why do we calculate them? There are 2 reasons that we bother with calculating formal charges. The first reason is that they help to confirm the correctness of a Lewis structure that we have drawn. If we draw a Lewis structure and then calculate the formal charges on a neutral molecule, we would find that in a correct Lewis structure, the formal charges must add up to 0. Again, that is for a neutral molecule. Also, in an ion or a polyatomic ion, the Lewis structure must have atoms that all add up to the charge on the ion. So for instance, if we have the sulfate ion, the SO4 2 negative ion, the formal charges in that ion after we've drawn our structure must add up to -2, or else we have drawn an improper structure. Furthermore, where formal charges are really useful is they help us to decide between Lewis structures when more than one is possible. We saw some examples in our Drawing Lewis Structures lecture where we had to decide between double bonds that attach to an O or double bonds that attach to a chlorine. If we run into this situation, then we typically calculate the formal charges on each atom in the structure and then use the following guidelines to decide which is the more proper structure. The more proper structure for a molecule will have more zero formal charges. So they will have more atoms with zero as the formal charge. If numbers other than zero are unavoidable, then the structure with the lowest formal charges are preferred. So if you draw one structure that works and it has a couple atoms with negative ones and positive ones, that would be better than another structure you drew that had atoms with positive or negative 2s and 3s. If you have atoms with formal charges beside each other, other than zero, it is preferable if they are of opposite charge. So if you have two atoms beside each other in a molecule, you should, and one is positive and one is negative, they should be beside each other. And then finally, negative formal charges should be found on your most electronegative elements. So when you see -1, -2, and -3 formal charges arise in molecules, the correct structures have those negative charges on atoms like chlorine and bromine. Here on this slide, we will look at an example of how formal charges can help us deduce a correct structure. We're being asked to determine the Lewis structure of carbon dioxide here on this slide. We start our examination of Lewis structures, as we always do, by counting the valence electrons we have to work with. Since this is CO2, I'm going to line out 1 carbon and 2 oxygens. Carbon has 4 valence electrons, and each oxygen will bring 6. That is a total of 16 valence electrons. Now we will decide on our central molecule. Out of the two choices, carbon and oxygen, carbon is the least electronegative, so we will make that our central molecule, and we will attach our oxygens with single bonds. Then we will fill out the remaining electrons around our atoms, around our terminal atoms, in order to complete octets. We've used 4 of our electrons already, meaning we have 12 left to use. So if we go ahead and put those 12 around each oxygen, we will fill their octets. At this point, we can probably see that while the correct number of electrons have been used and oxygens have full octets, our carbon has not satisfied his octet. So we will need to rearrange some of these electrons into multiple bonds in order to help carbon satisfy the octet. The first rearrangement would look like this. We would have our oxygen here and our carbon, and we would move our electrons down here into a multiple bond, in which case we would have a carbon dioxide structure that looks like this. So we've gotten closer to our octet on the carbon. We now have 6 electrons, but we're still not all the way to the 8. And it's at this point that formal charges will help us decide. We have 2 options for making the octet on the carbon work. We could either take one of these pairs and put it there to that carbon and arrive at this structure. But it's also conceivable that instead of doing that, we take this pair of electrons here and make a triple bond there instead and arrive at this structure. We could count and show that in both of these structures, 16 electrons have been used, and everyone, all of the involved atoms, has a satisfied octet. So how are we going to discern between which is the correct structure, this one or this one? Well, the answer is formal charge. If we calculate the formal charge on this carbon, we would find out that it is 0. If we calculate the formal charge on this oxygen, we would find out that it is 6 minus 4 minus half of 2, also 0. The formal charges on each of these atoms in this structure are zeros. If we calculate the formal charges on these atoms in our alternate structure, we would find that the carbon has a 0 formal charge. But then we would find that this oxygen has a 6 minus 2 minus 1/2 of 6, positive 1 formal charge. And this oxygen has a negative 1 formal charge. Because of our guidelines, we find that this would be the correct structure, because structures that have less numbers other than 0 are more correct than structures that have formal charges other than 0. We can see on this slide another example of where formal charges might come in handy. If we were asked to draw the Lewis structures of the thiocyanate ion with the formula SCN-, we might find that we have a difficult time predicting what the central atom is. We know that the central atom is supposed to be the least electronegative atom out of the choices, but sulfur, carbon, and nitrogen all have relatively closely matched electronegativities, and so there might be a question as to which one belongs in the center. Well, formal charges give us our answer. If we draw the 3 predicted structures, or the 3 allowable structures for thiocyanate, we could end up with what we see here, with formulas with, or structures with, the C in the middle, the nitrogen in the middle, or the sulfur in the middle. And then to determine which one is correct, if we wanted to be sure, we could calculate the formal charges on each of the atoms in that structure. We would then find that, like we've seen from our guidelines already, structures that have the lowest relative formal charges will be the correct structure. Because this one has more zeros than the other, and the only formal charge that does appear is a -1, while we see positive and -2s in the other structures, the correct structure for thiocyanate would be the one with the carbon as the central atom. One of the last things I want to mention about Lewis structures is an idea talking about resonance. Resonance is something that we see when 2 or more Lewis structures with the same arrangement of atoms can be written for a molecule or an ion. Then the actual distribution of those electrons is an average shown by the various Lewis structures. This is best displayed by a visual demonstration, which you will find on the next slide. And finally, here on this slide, we have some examples of compounds that form resonance structures. The first one there that you see is the carbonate ion. That is a CO3 That is a CO3 2- ion. And so if you were asked to draw the Lewis structure for this ion, you would find that any of these 3 structures drawn here would work. They all satisfy the octet rules. They all use the correct number of electrons, and they all have identical formal charges. So you can't decide which one is correct. They're all 3 correct. even though that bond is bonded, that double bond is bonded to different oxygens in each structure. What resonance shows, when chemists draw these resonance structures, they are showing that all of those bonds are equal. And so we draw each structure with arrows in between to show that all three are good structures. The important thing to keep in mind for resonance structures, and this is the questions you will see on it. If you see a question that says these are resonance structures, they will ask, how would you describe the bonds in these resonance structures? And what they want you to know is, even though we draw the double bonds separate from the single bonds, and then we draw the arrows to show that the double bond can be attached to any of the oxygens, that is not what is actually happening in the real molecule. What is actually happening in the real molecule is that double bond is somewhat spread out over each of the oxygens. So it's like each of them has a little piece of that double bond. And so the answer is, even though it's depicted with the double bond in different places, all of these bonds are actually the same length and the same strength, somewhere between a double bond and a single bond. We just don't have a good way other than this of representing that. So when you see these questions about resonance examples, just keep in mind that even though the bonds appear different, because the resonance structures are shown, that means the bonds are all actually the same, and they're somewhere between the single bond and the double bond that is shown.